Good afternoon. My name is Mark Carmen, and I'm a ninth grade geometry student. Today I'm going to tell you about my project, which is entitled The Circle-Square Continuum. The original problem is shown below. The figure below is created by inscribing circles and squares within each other. Find the total area of the shaded regions. To solve this problem, we have to look at this question as if there are actually two areas and not one. I'm going to call this larger group of, I guess you call them spikes. This larger group is going to be called Area 1, and then the smaller group of 4 spikes inside I'm going to call Area 2. If we take a look at the figure, there's actually a really important 45-45-90 triangle tucked away in the corner. We know that the hypotenuse would have to be radical 2, which means the side length of the first square is 2 and the side length of the second square is radical 2. This gives us the common ratio for finding side lengths as rad 2 over 2. This will become very important as we move forward. Like I said, there's actually two areas here in this figure, and to find the total area, we just have to add them together by taking the area of the square and then subtracting the area of the circle. So the total area turns out to be 3/2 times 4 minus pi, which actually equates to 3/2 of the what I called Area 1. For my first investigation, I wanted to see what would happen if you repeated this process. So you'll see on the left, there's the same figure, but this time there's 3 different layers or stages, and the figure on the right has 4 stages. Turns out the total area on the left side turned out to be 7/4 of the first area, and on the right side I got 15/8 of the area. This made me very curious because, 7/4 is kind of close to 2, 15/8 is suspiciously close to 2, so I got to wonder if maybe if I did this for long enough, would the actual shaded area ever reach an amount that was twice the size of Area 1. Well, in Investigation 2 I actually did just that. You'll see here that the figure has been reiterated in itself. Actually, it's only 12 times, but it looks like a lot more than that. That's kind of the great thing about, this technology that we have, is that I can actually throw this into a computer and generate this image, so instead of just talking to you about it, we can really visualize what it looks like. If I was giving this presentation 20 years ago, I literally have no idea how I would have shown you what this would look like, but now we can see it. It's only 12 stages, but imagine that this is n stages. It can go on as far as you'd like. N could be any number at this point, any natural number. So, remember that we said the common ratio for the side lengths of the squares was rad 2 over 2. That means that the common ratio for the areas would have to be 1 over 2. So I have here a geometric sequence formula which describes the areas, which also gives us a geometric series formula for adding up the areas together. We could simplify a little bit, and then we get down to this formula, which will actually calculate the total area given any value of n that we want. We don't have to just do 3 or 4, we could go up to 7 layers, or 17 layers, or 48 layers. And what's really cool is that this formula will verify the answers that I got for my first investigation. You see here is the area of the first 2 shaded regions, which is 3/2, A1, and then the area of all 3 regions when n was equal to 3 turned out to be 7/4, and so on and so forth. 15/8 would also work. The second really neat observation here is what happens as n approaches infinity. Take a good look at this total area formula. Well, if n were to approach infinity, you'd have 1 divided by 2 to a very, very large power. And 2 to a very large power in a denominator, with only 1 as your numerator, well, this expression here, this fraction, would ultimately approach, not equal, but approach 0. So you'd have 2 times 4 minus pi times 1 minus something that's really, really close to 0. So as n approaches infinity, s sub n approaches, does not equals, approaches 2 times 4 minus pi. That's exactly what I predicted would happen. It turns out that as n approaches infinity, the total shaded area approaches, but never equals, 2 times a1. So, I guess you could kind of achieve 2a1, you just have to do it forever. No, but seriously, to give you a visual idea of what's happening, if you took all of these areas as n approached infinity and just added them together, it would amount to approximately, it would never actually equal it, but it would approach 2 of these put together. The more stages you continue on, like the higher n is, the closer and closer you're going to get to actually having a total area that is twice a1. Well, this got me thinking, actually, because now that I'd solved this problem for area, it got me thinking about perimeter. In other words, what if I look at the perimeter of all of these little spike shapes? would it give the same result if I wanted to calculate the total perimeter of all those little blue spikes? It would make sense. I mean, if you think about it, if all of these areas turn out to be approaching 2 A1s, shouldn't the total perimeter do the same thing? I mean, it kind of makes sense. If you want to make 2 stop signs, you'll have 2 octagons, so you'll have twice as much area and twice as much perimeter. Well, let's find out. So here's the figure again, but this time we're going to be focusing on perimeter. Now, just to save some time here, I've already done the background work, and you can see it in the paper. Here's the formula, the geometric sequence formula for finding the nth perimeter. The first perimeter turned out to be 8 plus 2 pi, and this time the common ratio stayed as 1 over rad 2, because remember, that's the common ratio between each of the square side lengths. So if you throw this into your geometric series formula, very similar to the area result, the area of the perimeter, the total perimeter, approaches rad 2 divided by rad 2 minus 1 times the first perimeter, which is really strange because I predicted that this coefficient here would be a 2, yet it's not. It's this really, really strange and highly irrational number, which is approximately 3.414 times perimeter 1. And kind of here as a joke, I've shown you this. All of these perimeters, in other words, will... this really shouldn't say equals, I suppose, but visually, we can think of this as equating to 3.414 of the first perimeter. So remember, they're never actually going to be equal to each other, but visually, all of this perimeter amounts to about 3.414 of those, which is very, very cool, because it shows me that I have a lot to learn about infinity. I really thought that this perimeter would be twice, since that's exactly what the area did, but clearly that's not what's going on here. In fact, this number here has no, rational link to 2. It gets me really interested about these types of figures as n approaches infinity, and I look forward to learning about them more in the future. Thank you for your time today.